Let's now make the transition from continuous translational symmetry to discrete translational symmetry. So rather than having a structure that you can move over any possible distance and still end up with the same distance, you have a structure which you can only move over very specific distances. So let's give a one-dimensional example. Let's say you have a structure like this, some sort of grating-like thing, where this thing periodically repeats. And then you see if you translate here over a distance a, that you end up with the same structure, and that you can also translate over distances 2a, 3a, minus 2a, and things like that. So this is an example of a structure with one-dimensional discrete translational symmetry. So some terminology here. This distance here is sometimes called the period or the lattice constant. And you can also turn this into a vector if you want to take into account the direction over which you shift. And then you have a vector A, which is in our case, for example, something like this. And this is then called the primitive lattice vector if you have the shortest one over which you can move. So the primitive lattice vector. Okay. By the way, I use the term lattice here. So just a quick aside. What is actually a lattice? Well, a lattice is a linear combination of primitive lattice vectors, but a special linear combination in the sense that the coefficients, they're all integers. And also for each dimension in your lattice, you should have one primitive lattice vector. So in our case, we have the example of one-dimensional lattice. You can basically represent this by integer multiples of the shortest vector that you have, the A, the primitive lattice vector, and L, they are of course positive and negative integer values. So you end up with a set of points, a set of lattice vectors like this. And then you can repeat the same thing in 2 dimensions if you want, and so on and so forth. So that's a lattice. And it's also worth thinking about the following fact, namely if you take any 2 points in your lattice and you take a linear combination, an integer linear combination, I should say, of these points, then again, you end up at a point that's part of the same lattice. So this was a small aside about what a lattice is. So in our case, we have this structure with 1D discrete translational symmetry. So if you plot the refractive index profile as a function of the spatial coordinates, because of our symmetry, the following will be true. And also, of course, this will be true for integer multiples of our primitive lattice vector A. By the way, the refractive index profile that you periodically repeat, so in this case, the single tooth of this grating here, this is also sometimes called the unit cell. So this is the thing which you repeat periodically, the distribution of the refractive index profile. Right. So let's take stock of what we have. We have a situation where we have Maxwell's equations described by a theta operator, and then we have symmetries which are described by translational operators over a certain distance, and the distances over which we can translate here are integer multiples of a certain basic length. Now we know from previous videos that in that case, these 2 operators commute, right? And that leads to all sorts of interesting conclusions. So the question is, can you repeat something very similar to what we did for the case of continuous translational symmetry and use that to derive, for example, the relationship between the fields at a certain position z plus LA, and see how that relates to the field at an original position h of z. So just for notational simplicity, let's restrict ourselves to a one-dimensional scalar case. So pause the video and see if you can figure out what we should fill out here in this position. So we can actually follow exactly the same line of reasoning as we did for continuous translational symmetry in our particular case. And you remember that from a previous video where we said, okay, if you have 2 different translations, one over the distance d1 and another one over the distance d2, this is equivalent to a single big translation over the sum of the 2. And again, if you follow exactly the same line of reasoning as we did for the case of continuous translational symmetry, you basically figure out that what you should write here before h of z is exponential minus j kz LA. So the reasoning we did in the previous video is exactly the same. The only difference here lies in the fact that the distance over which you translate is different. In the previous case, for continuous translational symmetry, this could be over any possible distance d. Now, in our case, you can only do this for distances which are integer multiples of a. But otherwise, the line of reasoning that led to this conclusion is exactly the same. So now we can do a very simple manipulation. We can just say that L is equal to 1, and then we end up with saying that the field at position z plus a is just exponential minus j kz of a h of z. And that's a very interesting and famous theorem. This is actually the first form of Bloch's theorem. And Bloch's theorem relates the field at a certain position in your structure to the field at a position which is one lattice constant away. And the relationship is given by this multiplicative phase factor here. So these are the solutions that you can find in this case. And because this is Bloch's theorem, these are sometimes also called Bloch modes or Bloch states. Now, a very simple, quick and easy question. So we're dealing with periodic media. Solutions are Bloch modes. Are these Bloch modes actually periodic themselves? Yes or no? Well, many people think that Bloch modes are periodic because we're dealing with periodic media, but this equation actually clearly shows that we're not periodic, right? Because if this function were to have period a, then this coefficient here should be equal to 1. But in general, that's not true. So remember, Bloch modes by themselves are not periodic. Okay. Finally, just to wrap up, there's lots of similarities, but also subtle difference between continuous translational symmetry and discrete translational symmetry. So think a bit for yourself if you can really express what that difference is if you compare a Bloch mode in a periodic structure to a waveguide mode in a slab waveguide, for example. So see if you can articulate that difference. So what's going on for a Bloch mode? If you have a Bloch mode and you look at the field at a certain arbitrary position z, and then you move over the distance a, then you end up with the same field that you started with, but the price you pay for that movement, if you want, is a phase factor exponential minus j kz a. Okay. What happens if you have a slab waveguide? If you have a slab waveguide and you start with the field at a certain position z, and you move over a certain distance a, then you end up with the same field h of z, but you multiply by exponential minus j kz a. So far, so similar, right? It's exactly the same phase factor that you pick up. The only important and crucial difference is that for a slab waveguide for continuous translational symmetry, this equation actually holds for all possible distances a over which you want to translate, whereas this equation in a Bloch mode is only true if you multiply, if you move over distances which are multiples of the primitive lattice constant of the period a. So bear that in mind. They're very similar, but also very different in terms of the distances over which you can propagate. And then just a final piece of terminology, also for Bloch modes, you have this propagation constant kz, this wave number of the Bloch mode. So this is why it's also sometimes called a Bloch wave factor, right? So, but again, it's very similar to the kz of a slab waveguide. The interpretation is slightly different in the sense that it only works if you translate over integer multiples of a.